Okay, so welcome to the first afternoon session of the last day. So we will have 3 talks in this session. The 2 will be on site and then 1 will be online. So the first talk is functional encryption with secure key leasing by Fuyuki Katagawa and Ryo Nishimaki. And Ryo will give the talk.
Thank you for the introduction. I'm very happy to talk about our work, functional encryption with secure key leasing. So this is a short summary of our work. In this work, we introduce the notion of functional encryption, in FE in short, with secure key leasing and the single decryptor FE. And we also propose how to achieve these new notions. Let's start with reviewing the classical FE and its limitation. In FE, a setup algorithm generates a master secret key, and a key generation algorithm takes function f and the master secret key, and output a functional decryption key SKF. In public key FE, we at the encryption phase, we use the encryption algorithm takes public key and plain text X and output the ciphertext of X. In secret key FE setting, we need the master secret key for this encryption. And if we have a functional decryption key SKF, we can compute f of X from ciphertext or plain text X. This is classical FE. So the question is, can we cancel the power of functional decryption keys? So if we receive a functional decryption key, then we can compute f of X from the ciphertext of X forever. So even if we return a functional decryption key, it is meaningless because we can keep a copy of functional decryption key. So this is a big problem in a setting where valid users frequently changes, like a subscription model. So in cryptography, there is we can implement a revocation mechanism in some setting, and in particular, we have revocable FE. Right? It's done. The answer is no, because it is not perfect solution. Because we need to update all ciphertext to revoke a functional decryption key in revocable FE. We encrypt huge data today, so it is very inefficient to update all ciphertext. So even if we accept the inefficiency, there is still a fundamental problem. So the problem is we cannot prove we delete something in classical setting. So we can update functional encryption ciphertext, then a revoked functional decryption key cannot compute f of X anymore. However, there is no guarantee that all the ciphertext were properly deleted. If someone keep a copy of ciphertext, then the revoked functional decryption key still can compute f of X from copied old ciphertext. So this is a big problem. However, if we consider quantum setting, the situation completely changes. In general, it is impossible to copy unknown quantum state. The no cloning theorem said that there is no general procedure for copying unknown quantum states. By using this property, we can achieve public quantum money, program copy protection, and unclonable cryptography. In addition, we can prove that we delete quantum state by using the uncertainty principle. By using this property, we can achieve secure software releasing and cryptography with secure deletion. So this is the power of quantum information. So in this work, we focus on functional encryption, and we introduce the notion of FE with secure key releasing, where we can delete functional decryption keys. And we also introduce the notion of single decryptor functional encryption, where functional decryption keys are copy protected. So in FE with secure releasing, the big difference is a functional decryption key is quantum state. And the key generation algorithm also generates a verification key for each functional decryption key. This verification key is either private or public. In this work, we consider all verification keys are private. In addition, we have two additional algorithms for FE with secure key releasing. One is certification algorithm, and the other is verification algorithm. The certification algorithm takes a functional decryption key and output a certificate for proving deletion. So we can generate a certificate for deletion. The verification algorithm takes a certificate and the verification key and output it is valid or not. If the certificate is valid, then the functional decryption key was securely deleted, and we can no longer obtain f of x from encryption of plaintext x. This is FE with security releasing. Now we consider the security game for secret key functional encryption with secure key releasing. In this game, the adversary output the pair of challenge plaintext x0 and x1, and the challenger returns the challenge ciphertext of x0 or x1. And the adversary tries to guess the correct bit. During this game, the adversary can send key queries. The adversary sends function f and the availability bound n to the challenger, and the challenger returns the functional decryption key for function f. I will explain the meaning of the availability bound n later. Here we consider private verification. So the adversary can send the verification queries. The adversary sends the certificate. Then the challenger returns the certificate is valid or not. So in the classical FE, the adversary can send a key query f such that f of x0 is equal to f of x1 to prevent the trivial win. However, in this game, the adversary can send a function f such that f of x0 is not equal to f of x1 if certificate for function f is valid, because in that case, the functional decryption key was deleted. So we consider a secret key functional encryption setting. So the adversary can send the encryption queries to the challenger. Then the challenger returns a ciphertext. And the adversary can send any encryption queries before deletion. This is the meaning of the availability bound. So if so before the adversary output a valid certificate for function f, the adversary can send any encryption queries. After the adversary output a valid certificate for f, then the adversary can send encryption queries as many as it wants. This captures this security game capture secure deletion Because if the adversary still has the function direction key is not deleted, then the adversary can trivially win the game. Okay, so let's I briefly explain the notion of single decryptor functional encryption. The syntax of single decryptor FE is almost the same as the standard FE, except that the functional decryption keys are quantum state. However, unlike FE with secure key racing, this primitive does not have explicit returning process. We just guarantee that the functional decryption key are copy protected. So in the security game of single decryptor FE, the adversary is given a functional decryption key for function F and output to possibly entangled pirate decryption programs and a pair of plaintext X0 and X1. Then we test these pirate decryption programs by sending a challenge ciphertext to each decryption program. So if both programs can correctly distinguish the challenge ciphertext, even if the adversary output the plaintext X0, X1 such that f of X0 is not equal to f of X1, then if the adversary can, these two programs cannot distinguish the challenge ciphertext, then we succeeded in preventing copying functional decryption key. Because if the adversary can succeed in copying functional decryption key, the adversary trivially wins this game. This is a single decryptor functional. Okay, so let's see how to achieve a secret key FE with secure racing. And first, I explained the building block of our construction, encryption with certified deletion. This is a kind of dual of encryption with secure key racing. In this primitive, encryption algorithm is quantum and takes plaintext M and secret key, output quantum ciphertext and corresponding verification key. And we also have a deletion algorithm and verification algorithm. The deletion algorithm takes quantum ciphertext and output proof of deletion. It's a certificate for deletion. And the verification algorithm takes a certificate and verification key, output the certificate is valid or not. Now I explain the security notion for certified deletion for secret key encryption. The adversary output a pair of challenge plaintext M0 and M1. The challenger returns a challenge ciphertext of X0 and X1. Like if it is secure key racing, the adversary can send the verification queries. And if a certificate for the challenge ciphertext is valid, then the challenger reveals secret key to the adversary. And the adversary can also send the encryption queries. This is because this is a secret key encryption setting. So this captures secure deletion of ciphertext, because if the adversary still has the challenge ciphertext, then by using secret key, the adversary can trivially win this game. Okay. And we can achieve this fantastic primitive by using standard secret key encryption, classical secret key encryption, which is based on one-way function. Now I explain how to achieve zero ability bound secret key FE with secure key racing by using classical bounded secret key functional encryption and SKE with secure certified deletion. At the key generation phase, we first generate a classical functional decryption key for function F, and then we encrypt this classical functional decryption key by using encryption with certified deletion. So our functional decryption key is a quantum ciphertext. And the verification key of SKE with certified deletion is our verification key. At the encryption, we first encrypt plaintext X by using classical secret key functional encryption. and we append the secret key of SKE with certified deletion. This is our quantum ciphertext. Oh, no, classical ciphertext. Classical ciphertext. So the security behind our construction is as follows. If we delete functional decryption key, this is the quantum ciphertext of SKE with certified deletion. If we delete this quantum ciphertext before we given the ciphertext, which include the secret key of SKE with certified deletion, then we cannot get a classical functional decryption key for function F. So thanks to the certified deletion security of SKE with certified deletion, even if the secret key of SKE with certified deletion is revealed, we have no idea about the deleted functional decryption key. However, if we given the ciphertext before we delete the functional decryption key, then we can recover the classical functional decryption key. So we can only achieve zero availability bound scheme. Our goal is achieve n availability bound scheme where n is a fixed polynomial. In classical setting, we can obtain bounded collision resistant functional encryption from one bounded scheme. So it is natural to try to use the known transformation technique. However, we cannot apply the known technique because our starting point is zero availability bound scheme, not is one bounded. So, however, there is an observation. If we relax the setting, it is we can achieve any availability bound scheme in more precisely. So, if we consider, if we accept stateful encryption and non-negligible security bound, then we can achieve an availability bound scheme in the static setting where n is fixed at the setup phase. So non-negligible security bound means the security advantage of the adversary is 1 over polynomial, which is non-negligible. We call this security 1 over alpha security. However, we want to remove this restriction. So somehow we need to amplify the security and improve the security bound. So we transform zero availability bound scheme into n availability bound scheme with negligible security via a few transformations. First, we obtain n availability bound scheme with stateful encryption and static small n over capital N security by using simple parallel repetition. Second, we obtain n availability bound with static negligible security by using set homomorphic secret sharing. And finally, we obtain our goal n availability bound with negligible security by using parallel repetition with some efficiency property. In this work, we focus on the second transformation because it is the most interesting part. So we omit the other two transformations in this talk. Please see the paper for the detail. And in the second transformation, we use the half security, which is obtained by setting capital N to 2 times small n. In homomorphic secret sharing, we can generate a share of input X and a share of function F. And from each share, we can compute the share of the output F of X. By collecting all shares of the output, we can recover the output F of X. So, and even if we are given all shares of X and F except one share of input X, we cannot tell whether the encoding come from X0 or X1. This is the homomorphic secret sharing. And we use M instances of half secure scheme to achieve our FE. So by using FE, we encrypt each share And we also generate a functional declaration key for each share of function f. By the functionality of FE, we can compute each share of the output by using from each instance of FE. And we can also recover f of x. And each FE is half secure. So at least one instance of these M instances is secure with probability 1 minus 1 over 2 to the m. So our scheme is secure, and the security bound is 1 over 2 to the m, which is negligible. So this is the high-level overview of our second transformation. So, and in the previous slide, I explained to explain our essential idea, we use the homomorphic secret sharing. However, this primitive needs the irreducibility assumption. But in our actual construction, we use a weaker variant, set homomorphic secret sharing, which can be obtained from standard one-way function. So our construction is based on one-way functions. So I oversimplified the construction to explain our idea. Let me summarize my talk. In this work, we presented the new notions for functional encryption, FE with secure key releasing, and single decryptor FE. We also proposed the bounded collision resistant secret key FE with secure releasing from one-way functions. Although I omit the construction, we also propose the collision-resistant single decryptor public key functional encryption from indistinguishability obfuscation and one-way functions. That's it. Thank you for your attention.
So we have time for questions. Any questions online? No. Maybe I'll ask a simple one. Can you comment on the possibility of getting maybe public verification?
Yeah, it is a very nice question. So yeah, I think it's possible. And if we use some stronger conjecture, it is known that we can achieve public verification. However, but at least we need a very strong assumption or conjecture. So it is open to achieve a public verification from standard assumptions.
I see. Thank you. Yeah, so let's thank the speaker again.
Thank you.
Okay, so let's move to the second talk. The title of the second talk is Classically Verifiable NIZK for QMA with Preprocessing. And it's by Tomoyuki Morime and Takashi Yamakawa. Takashi will give the talk.
Thank you for the introduction. I'm Takashi, and I will talk about this work with Tomoyuki. So it is believed that quantum computers are more powerful than classical computers. Then it is natural to ask if we can verify the correctness of quantum computation by using classical computers. And it has been a long-standing open problem in the field of quantum computation. And in 2018, Mahadev resolved this problem affirmatively by using the LW function. After Mahadev's breakthrough, there are a lot of follow-up works like making Mahadev protocol, the soundness amplification for the protocol and round reduction, or a non-interactive zero-knowledge version of Mahadev protocol, or succinct argument version. And especially in this work, we focus on non-interactive zero-knowledge NIZK for QMA. And here, the QMA is just a quantum version of NP, or more precisely MA, where the richness and the verification algorithm can be quantum. And I remarked that even though we consider such a quantum language, but we still require the verification of the NISQ to be classical. And there were several works about existing works about classically verifiable NISQ for QMA. And first, I reviewed work by Asiacrypt et al. And so in NISQ, we intuitively, NISQ is an interactive protocol between a prover and verifier, where a prover can non-interactively prove some statement is true in such a way that verifier doesn't learn anything beyond the correctness of the statement. And it is easy to see that that is impossible in the plain model. And so we have to introduce some kind of setup assumption. And in this work, I mean, in ACDH20, they consider this kind of setup where the trusted party first generate a correlated proving key and verification key and send them to the prover and verifier respectively. And formally speaking, we require the protocol to satisfy the three properties: completeness, soundness, and zero knowledge, as usual. And the good thing of this protocol is that this is based on standard assumption, which is the LW assumption, and also both the setup and verification algorithms are completely classical. On the other hand, drawbacks of this protocol is that it is in the secret parameter model where the trusted party has to generate a correlated proving key and verification key. And also it relies on random oracle. And also it only satisfies computational soundness and computational knowledge. And let me review another existing work of classically verifiable NISQ for QMA, which is by Danger et al. And in their work, they consider a different kind of setup model. And namely, so we consider some setup algorithm that publishes common reference string to both prover and verifier. And in addition to that, verifier has to send some quantum information to the prover as a preprocessing. And after this setup, the prover can non-interactively generate proof, I mean classical proof. And the good thing about this protocol is that it is based on standard assumption, LW assumption in the standard model. And also the online verification is classical. I mean, online verification means the verification after receiving the proof by. On the other hand, apparently the verifier has to have some quantum power because it has to send quantum information at the processing phase. And also, again, it only satisfies computational soundness and computational knowledge. And the ultimate goal in this direction is to construct classically verifiable NISQ for QMA in the theoretic model, where the trusted setup only generates a common reference string and just publish it to everyone. And this is the ideal model, but unfortunately, there is no known construction from standard assumptions, and even with quantum verification. And there is one heuristic construction of such a NISQ from obfuscation by Bartek and Malabota, but we don't have a security proof in the standard model. And this problem is a very challenging problem. So in this work, other steps toward this goal, we find new trade-offs among assumptions, security, and models for classically verifiable NISQ for QMA. And especially, we give three new constructions of classically verifiable NISQ for QMA with incomparable features. And from now, I will explain them one by one. And the first construction looks like this. For this construction, we consider a setup where that generates a quantum proving key and the classical verification key, and send them to the prover and verifier respectively. And after this setup, the proof is classical and also verification is classical. And we proved that our scheme satisfies both statistical soundness and statistical knowledge without assuming any assumption. And you might think that this is too good to be true, but actually, this is possible because of such a very strong setup assumption where the setup algorithm generates a correlated quantum proven key and verification key. And actually, in such a setting, it is already known that unconditionally secure NISQ for NP is possible in the classical setting and also in the quantum setting. If we allow the verifier to be quantum, it was already known that NISQ for QMA in such a model was possible. So we can consider our construction as a variant of the protocol by BG20, where we replace the quantum proof with classical proof at the cost of making the proving key quantum. And our second construction works in this kind of model. And this model is actually exactly the same as the model of CVZ20, if you remember. So I will explain that again. So as the first setup algorithm generates a common reference string and that just distributes it to both parties. And in addition to that, verifier generates a quantum processing message. And we prove that our construction is a dual mode NISQ under the LW assumption. And this means that there are two computationally indistinguishable modes. And the one of the modes is the binding mode, where statistical soundness holds. And in the other mode, which is the hiding mode, the statistical knowledge holds. And this is a strict improvement of CVZ20 because this is exactly in the same model based on exactly the same assumption, but they only proved computational soundness and computational knowledge. And they explicitly mention it open to make either of them statistical, and we resolve this problem. Our third construction is in this model. Prover and verifier share some entangled quantum states as a setup. And we call it the bell pair model. And we construct NISQ for QMA in such a model. And so this such a NISQ was an open problem posed by Broadbent and Grillo, and this also resolved their open problem. And we show that our construction satisfies computational soundness and computational knowledge in the quantum random worker model. Okay, so these are three constructions which we construct in this work. And from now, I will briefly explain the techniques. So before explaining our construction, let me introduce some technical tools. The first is locally simulatable state. And suppose that we have some state domain X and the witness W for some QMA problem. Then we can generate some special state, quantum state called history state. And we require the following two properties for history state. First, there is some verification algorithm and some alpha beta with inverse polynomial gap that satisfy the following. First, if X is the ES instance and verification takes the honestly generated history state, then the verification accepts with the probability at least alpha. On the other hand, as a soundness, if X is a no instance, then for any quantum state psi prime, verification accepts with probability at most beta. And as a third property, verification algorithm measures at the most C qubits of the history, where C is some constant, and especially in the paper, C is said to be 5. And as additional property, we require local simulatability, which means that any C qubits of history state can be efficiently simulated from X without using the witness. And the work by Broadbent and Grillo constructed showed how to generate such a history state. Locally simulatable history state from any statement and witness pair of QMA problem. So based on such a locally simulatable history state, they constructed needs for QMA in the secret parameter model as follows. So let n be the length of the history state. And then the setup algorithm first generate n keys k1 to kn of quantum one-time path. Then also choose some subset S of size C, which is supposed to be the subset on which verification algorithm measures. And then the setup algorithm sends K1 or keys K1 to Kn to the prover as a proving key, and only sends Ki corresponding to the subset S to the verifier as a verification key. Then for proving some QMA statement, the prover first generates history state corresponding to X and W, and then encrypt this history state by using the key of the quantum one-time path. And because prover is encrypting quantum state, so the ciphertext is also quantum. And then the verifier decrypts the corresponding part of the history state, which corresponds to the subset S. And by recovering that part of history state, it can run the verification of the history state because the subset S is defined to be the subset on which verification has to measure the history state. And it is easy to prove that this construction satisfies completeness and soundness by using those of the verification algorithm of the history state. And there is only an inverse polygap, but that can be easily amplified by using parallel repetition. And for their knowledge, this also simply follows from local simulatability. And this is the starting point of our first construction. But our motivation is to achieve classical verification. But apparently, this is not classically verifiable because proof itself is quantum. And we want to make the communication classical at least. And for this goal, we rely on quantum teleportation. So very roughly speaking, quantum teleportation is a technique to replace some quantum communication with classical communication, assuming that the two parties share some entangled state from the beginning. And so this is exactly what we want to do. So let's try to apply quantum teleportation to the broadband-Greer construction. So the result looks like this. So by using the quantum teleportation, now the communication between the prover and verifier becomes classical. On the other hand, for using the quantum teleportation, we have to assume that the prover and verifier share some entangled state. So this means that verifier has to keep some quantum state to run this verification protocol. This means that the verifier is still not completely classical. And here we make another observation. We observe that the verification algorithm of the history state actually only performs measurements in the Pauli basis. And this commutes with quantum teleportation. Or more precisely, if you are familiar with quantum teleportation, recall that for quantum teleportation, the receiver only has to correct Pauli errors. So such a correction of Pauli error commute with measurement in Pauli basis. So our idea is to let the setup algorithm do the measurement as a setup phase. And as a result, our first construction looks like this. So before doing the quantum teleportation, the setup algorithm first measures the verifier's half of the entangled state to get some measurement outcome. And this classical measurement outcome is used as a verification key. So as a result, the verifier now becomes completely classical. And this is our first construction. Next, I briefly explain the idea for our second construction. And second construction is based on the first construction. And here I describe first construction. And for the first security of the first construction, the following two properties are important. First, for soundness, prover should not know the subset S. And second, for zero knowledge property, verifier should not know Ki for I that doesn't belong to S. And in the first construction, we ensure these properties by relying on trusted setup. But it is easy to see that this property, this can be actually exactly what can be achieved by using oblivious transfer. So our idea is to simply replace the correlated key generation with the oblivious transfer. And especially by using dual mode oblivious transfer based on LWE, or we can get dual mode NISQ. And this is our second construction. And our third construction takes a little bit different route, but the basic idea is similar. So for our third construction, we start from 3-round public coin zero knowledge for QMA, where the first message is content. And this is also proposed by Broadbent and Gurulok. And the well-known technique to convert 3-round protocol into non-interactive protocol is the Fiat-Shamir transform. However, Fiat-Shamir transform doesn't work if the first message is content, because in Fiat-Shamir transform, we have to hash the first message to generate the second message. But we don't have a good hash that takes the content message and that hash to the second classical message. So we cannot directly apply Fiat-Shamir transform. And our idea is again, apply quantum teleportation to make the first message classical. And by using quantum teleportation, now the first message becomes classical, so we can simply apply Fiat-Shamir and we can rely on the known techniques in the quantum random model to prove this is indeed secure NISQ. And because we are now using quantum teleportation, so we have to assume that the prover and verifier shares entangled state as a set X. This is why our construction is in the Bell pair model. And this is a summary, and this is a comparison table among classically verifiable NISQ for QMA. And the remaining very important open problem is again constructing NISQ for QMA in the theory model from standard assumptions. And even with quantum verification, this is a very difficult problem, and this is a very important problem. And that's it. Thank you for your attention.
Thanks. And yeah, we have quite some time for questions.
Thanks for the talk. So for the third construction, the security assumption is the QRAM. Does this mean, and the security is computational, does this mean there is a bound also on the runtime of the adversary, or only the number of queries is bounded?
Thank you for the question. This only bounds the number of queries.
Thank you.
Any more questions? Okay, so thanks Takashi. So the third talk is given online. Okay, so The title of the third talk is General Properties of Quantum Bit Commitment by Jen Yun, and Jen will give the talk online.
Okay, can you hear me? Yeah, thanks for the introduction. Good afternoon, everyone. The title of my talk today is General Properties of Quantum Bit Commitments. I'm Jin Yan from Jinan University. So the story begins with, since our world is quantum, we can ask the following motivating question. Can we base unconditional quantum cryptography solely on principles of quantum mechanics? Stephen Wisner might be the first person to explore this possibility. Back in early 1970s, he studied quantum money. Inspired by Wisner's idea, two primitives ending with two different fates were intensively studied in early days of quantum cryptography. The first primitive is a quantum key distribution. Brassard and Burnett and Brassard, they independently have developed two slightly different quantum key distribution protocol, which was finally proved unconditional secure. However, this is unfortunate for quantum bit commitment. All proposed schemes in early 19th were finally broken. So the possibility of quantum bit commitment was finally settled in the middle 90s. Mayers and Law and Chow independently have proved that QBC is impossible. This is a really big blow to ambitious quantum cryptographer. Since then, QBC seems dead. In the subsequent almost 2 decades, there was little progress studying QBC. Until recently, quantum bit commitment revives. And also in the Diffie-Hellman sense. That is, we compromise to introduce computational hardness studying computational QBC. This is ironically in contrast to the original motivation of studying quantum cryptography unconditionally. However, this is actually the starting point of this work. So in this work, we propose to base quantum cryptography on computational basis QBC, or its two equivalent complexity theoretic objects induced by it. And we remark that several exciting and somewhat surprising results are obtained towards this research direction in this and subsequent work. So let me go into the detail. I will first introduce canonical QBC and its two complexity theoretic formulations. We first refer to these two complexity theoretic objects. The object one is two ensembles of efficiently generated quantum states that are statistically far in trace distance, but computationally indistinguishable. One may compare it with its classical counterpart, namely two ensembles of efficiently constructible probability distributions that are statistically far, but computationally indistinguishable. Those rags show that this classical counterpart is equivalent to one-way functions, and in turn, a pseudo-random generator. So this first object can somehow wield as quantum computational indistinguishability or pseudo-randomness. This object is also known as EFI in a subsequent work. Now let's turn to the second object. It can be viewed as a computational negation of Ullmann's theorem. Consider these two quantum states. They are identical in the register C, but different in the register R. So Ullmann's theorem ensures that there exists a unitary U that can transform the left state to the right state. Here, we impose some complexity assumption that such U is not efficiently realizable. So this gives the second object, which we just call it woman. It is two ensembles of efficiently generated quantum states, such that their reduced states in the register C are statistically closed, but there does not exist efficiently realizable U performing on register R that transform the state from one ensemble to the state from the other. So this second object can be weighed at some complexity of transformation. So now we have two complexity theoretic objects that seem quite different in nature. EFI assumes no quantum polynomial time distinguisher, while woman assumes no quantum polynomial time transformer. And the second result I introduce in this talk is EFI and woman are equivalent. That is, EFI exists if and only if woman exists. But how to relate these two objects together? After all, they seem different in nature. The answer is they can be unified via canonical non-interactive quantum bit commitment. So let me illustrate their relations by this picture. We have EFI and woman. If you look closer at this EFI, it is just actually canonical computationally hiding statistically binding QBC in disguise. And similarly, this woman is just a canonical statistically hiding computationally binding QBC in disguise. So, in this work, we establish the equivalence between these two flavors of canonical QBC, and in turn, EFI and woman. So seeing from cryptographic perspective, we have two flavors of QBC. While seeing from the complexity theoretic perspective, we have EFI and woman, respectively. Oh, sorry. So I have not talked about the canonical QBC, so let me introduce it in greater detail. They can be represented by Q0, Q1, an ensemble of polynomial time, a uniformly generated unitary quantum circuit pair. To commit a bit B, we perform QB on C and R that are initialized in all 0 qubits. In the commit stage, we just send the register C to a receiver. And in the reveal stage, to open B, we send the register R to the receiver, who will perform the inverse of QB on C and R to check if they return to all 0 states. If yes, accept, reject otherwise. We note that its opening is canonical in the sense that it makes use of the reversibility of quantum computation to verify the sender's computation in the commit stage. One can compare it with its classical counterpart. For classical canonical opening, the sender sends its random coins used in the commit stage to the receiver, who will check that these coins explain or are consistent with the sender's message in the commit stage. So let me introduce the security of canonical QBC. The hiding is simple. It just says the commitment to 0 and the commitment to 1. Their quantum states in the register C. These two states are indistinguishable. Either statistical or canonical or computational indistinguishable. Its binding property, which we call honest binding, says that any malicious sender cannot open an honest 0 commitment or 1 commitment at 1 or 0. We highlight that Here, the sender is honest in the commit stage, but can cheat, deviate in an arbitrary way in the reveal stage. That's why we call it honest binding. Formally, for any unitary U, maybe unbounded or polynomial size bounded, perform this U on quantum state Q00, and the resulting state is almost orthogonal to Q10. We know that either the hiding or the binding properties should be computational, since QBC is impossible unconditionally. So we have two flavors of QBC with just one-sided statistical security, either statistical hiding or statistical binding. So our second result can be restated as canonical QBC is symmetric. That is, canonical statistically binding QBC exists if and only if canonical statistically hiding QBC exists. Okay, so let me talk about a little bit of history about canonical QBC. It comes from the study of complete problems for quantum statistical or perfect zero knowledge and more general quantum interactive proofs. Whose study is initialized by Wadan or Watchers. Let's look at the complete problem for quantum statistical zero knowledge proof. It is an ensemble of polytime uniformly generated quantum circuit pair Q0, Q1 performing on C and R, such that the trace distance between low 0 and low 1 is at least 2/3. This is for yes instance, while for no instance, their trace distance is no more than 1/3. We know that this is already gives an instance-dependent statistically hiding and statistically binding canonical QBC scheme after some polarization. Okay, this is the takeaway message I would like to send to you. Canonical QBC has two clean and simple to state complexity theoretic formulations that turns out to be equivalent. Okay, next, let me talk about the complexity assumption in Mini-Q-Crypt and its relation with our work. Impagliazzo have identified 5 possible classical words and claim that we live in one of them, but unfortunately, we do not know which one. In this work, we focus on this Mini-Crypt word, and we study its quantum counterpart, that is Mini-Q-Crypt, allowing both quantum computation and communication. In the classical Mini-Crypt word, the basic assumption is one-way functions, based on which we have a bunch of important primitives listed here. Turning to the quantum counterpart, Mini-Q-Crypt, besides what are left, but quantum secure, we in addition have oblivious transfer and quantum money. But it is open what is the basic assumption in Mini-Q-Crypt word. There are already 2 candidates. The first candidate is natural, and namely quantum secure one-way functions. And more recently, there is a second candidate, namely pseudo-random quantum states. And we know that there is a black box separation between these 2 candidates. In this work, we propose yet another candidate for the basic assumption in Mini-Q-Crypt. It is actually a complexity assumption with 3 equivalent formulations. First is canonical quantum bit commitment with one-sided statistical security. The second is EFI, can be viewed as a quantum equivalence of classical one-way function or pseudo-randomness. And the third is Woolman, can be viewed as the computational negation of Woolman's theorem. And with the first result I will introduce in this talk can allow us to close out this canonical word. We prove that quantum bit commitments exist if and only if canonical quantum bit commitments exist. Actually, we prove the following Round-Collapse theorem. It states that if a quantum bit commitment scheme is secure against the purification attack, or equivalently, its purification is semi-only secure, then it can be compressed into a scheme of the canonical form. This theorem proof is very simple, but it has many impressive features, which I do not have time to talk about in this talk. And the main contribution, technical contribution of this work is we study this security against the purification attack for the purpose of application of this Round-Collapse theorem, which I will skip here due to the time limit. In this follow-up work, it allows us to close out this restriction for one-sided statistical security. So seeing from this, you can see that the quantum bit commitment, this notion is very robust. So there are several evidences or reasons to support our proposal of basing quantum crypto on QBC. The first is, as just said, the notion of QBC is very robust. The second is the formulation of two equivalent complexity theoretic objects are clean and simple to state. They are suitable to serve as a complexity assumption. A third is EFI has a classical counterpart that is well-known equivalent to one-way functions. The fourth is QBC is weaker. It can be constructed from both quantum secure one-way functions and pseudo-random quantum states. The fifth is that QBC is not only sufficient, but also necessary for some important primitives, including a quantum zero knowledge and oblivious transfer. In contrast, it is unclear if one-way functions or pseudo-random quantum states are necessary for cryptographic applications. So let me conclude my talk with these pictures. We know that in other work, we know that from quantum secure one functions and pseudo-random quantum states, we can construct QBC or QBC of the canonical form. In this work, we establish these two equivalences, namely the equivalence between QBC and QBC of the canonical form, as well as the equivalence between two flavors of QBC. So it implies that from these two assumptions, we can construct a canonical QBC. And we also observe that two flavors of canonical QBC are equivalent to EFI and Woolman. And we propose to study all these bunch of equivalent objects as the basic complexity assumption in Minikube. Last, let me mention some open problems that interest me most. The first is, can the computational binding error of a canonical QBC be reduced, say from 1/2 or even inverse polynomial to be negligible, where parallel repetition? This question regards quantum hardness amplification, and I think it can be viewed as an amplification of one-wayness in the classical world. The second question is, it is interesting to explore whether QBC conversely imply pseudo-random quantum states of any sort. And in my opinion, this can be viewed as a quantum counterpart of a classical pseudo-random generator. And the third question is, can QPC serve as the foundation of Qcrypto? Let it find more applications of QPC and show that many other cryptographic applications conversely imply QPC. Okay. Okay, I do not have much time to talk about recent developments. So let me stop here. Thanks for your listening.
Yeah. So
So any
thanks.
question?
And,
Yeah.
Any questions? So actually, we do have like 5 minutes left for the session. So if you want, you can maybe tell us about the next slides.
This last slide, you mean?
Yes.
Okay. So so in this follow-up work, they explore more equivalence between quantum crypto and the QPC, and put more equivalent objects in this bucket. We have shown that a bunch of equivalent objects. And in this second paper, they explore yet another candidate complexity assumptions, which they called one-way state generator. And it's open whether it is equivalent to QPC. It's open, okay. But there are some recent progress towards this question. And in this third paper, they study quantum state commitments. They discover, in my opinion, rather surprising hiding binding duality, which can explain the symmetry for QPC established in this paper from a higher level. And in this first paper, inspired by equivalence between swapping and distinguishing, they give a much more efficient compiler for the symmetry of QPC, just using another single qubit. You can see our paper. Our paper use prove this symmetry via quantum oblivious transfer, which is very complex in comparison. Finally, in this work, Braskowski explore cosmology and crypto by replacing the use of quantum scale one-way functions in previous study with this EFI or QPC. And he established showed that this cosmology and crypto are equivalent. That's some exciting work just happened in September and October. A bunch of papers uploaded online. Yeah.
Okay, thank you. So let's thank again and all the speaker of the session again.